Welcome to the Z-mat training session series. In this session, we are going to learn about the Z-mat Abaqus interface features. For this, we are going to use a cube geometry meshed with hexahedral elements, as you can see it here on the screen. To illustrate the Abaqus Z-mat capabilities, we use two Abaqus simulations using the same geometry and mesh data. However, one of the Abaqus simulations, namely cube_abaqus.enp, uses the native Abaqus material definitions for elastic material, while the cube_abaqus Z-mat elastic uses the Z-mat elastic material definitions. The input files for these two are as shown on the screen. Here we see that the two Abaqus input files differ in the material block definitions. The file on the right side points to the Abaqus simulation file using native Abaqus material definitions and is given the name elastic, which is arbitrary. On the left side, we see that the material assigned is Z-mat elastic. This name points to the ASCII file containing the Z-mat material definitions. The name of this file is arbitrary as well. We will first discuss the native Abaqus simulation, which uses the Abaqus elastic material definitions. As you can see here on the screen, it's a typical Abaqus input file which consists of various blocks such as nodes, elements, materials, steps, output definitions, etc. Now let's import this Abaqus model into the Abaqus viewer to visualize the various blocks. For this, we use the Abaqus CAE interface. So if we need to import the model, the input file. So as you can see here, this is the meshed cube geometry that we have already discussed about in the problem definition. If we expand this model definition, here we can just see the different blocks that we have seen in the input file. Here the blocks such as parts, material definitions. In the material definition, as we have already discussed, it's an elastic material. So if we click on this, we can see that it's a material defined by the Young's modulus and the Poisson ratio. Also, you have other blocks such as sections, assembly, steps. This is an important block, as you can see here. In the steps, we can look at the boundary conditions that are being applied. So in this case, we are applying two sets of boundary conditions. The first one, where you basically, as you can see here on this on the graphical interface, here we are applying a displacement boundary conditions that is on the face bottom, where you fix all the displacements in directions 1, 2, and 3. So this is a fixed face of the bottom. That's one set of boundary conditions. Coming to the second set of boundary conditions, as you can see here on the screen, you're applying on the region called top, you're applying a displacement in the direction u3 of magnitude 0.1, as you can see here. So this is about the steps block. And then if we move on, you have many other blocks in this case. But what's important for us in this case, for the Z-mat Abaqus interface training, is about the material definitions. So that's the one which we are using here as elastic. Now let's run the simulation. We will only be using the command prompt to launch our simulations. For this, we need to open a command prompt and change the directory to the location where we have the files from the Z-mat Abaqus training material. So in this case, I've opened a terminal, a command prompt of Windows, and I'll browse. So in order to launch the simulation, we need to use the Abaqus command as shown on the screen. So the command is Abaqus followed by the switches interactive, and then followed by the job name. In this case, it is cube Abaqus INP. So there are, for a full list or exhaustive list of all the command switches of Abaqus, you can refer to the online documentation. As we can see, Abaqus has printed some information on the screen, like it is running the pre-processing, then followed by the Abaqus standard analysis processing, and at the last it says that Abaqus job has been completed. The execution of Abacus simulation creates various files like the STA file, the message file, the ODB file, the DAT file, and various other files. The ODB file is the output database file that contains the results of the simulation. We can now visualize the results of the simulation using Abacus GUI. For this, we can load the ODB file of the simulation. For this, you can just say open and you can choose your ODB file format and then load the qabacus.odb that was just created as a result of execution. Here we can see that this is the cube, and now in order to visualize some fields, it's possible by clicking on these plot contours on deform shape. As you can see here, this is the von Mises stress. You can also visualize. You can play around with different options of visualization available within Abacus GUI interface. You can also animate your results. So this is about visualizing your results, Abacus results using the Abacus GUI. Before we move on to the Abacus simulation using the Z-mat material interface, as a first step to introducing the Abacus Z-set interface, I would like to discuss the capability of visualizing the Abacus results, that is the ODB file, using the Z-master interface. As a first step, we need to define the environment variable Abacus root pointing to the Abacus installation directory. This can be done as follows. You need to edit your environment variables, and here in your under system variables you can create a new variable called Abacus root. Yes, Abacus root. And this location, the value of this variable should be pointing to the installation directory of your Abacus. Just browse directory and you can, in my case, I've installed it on C drive, Simulia, ST products. Yeah, so this is the location. So once you have created this, you can click on OK and close it. You can already see that you have existing ZSet related system variables like ZSet path, and also the path variable which is being appended with the ZSet installation Windows 64 directory as well. So these are as a part of standard ZSet setup procedures. In addition, now we have added the Abacus root as a new environment variable to be able to handle the ZSet Abacus interface. So once you're done with that, you can click on OK, close it. And now we can launch the Z-master interface to visualize the Abacus results as follows. The command is ZODB with the switch -G followed by the name of the ODB file which you want to visualize. As you can see, it has opened up the Z-master interface. And this is the mesh, as you can see here. This is the mesh, and now you can actually visualize the results. For example, von Mises stress. We can actually compare it with the ones which was visualized by Abacus. For example, here you can put them on side by side here as shown on the screen here. So on the left we have the standard Abacus CAE GUI interface, and on the right we have the Z-master interface where we have loaded the Abacus ODB here. As you can see, there's a various information being printed here in the Z-master interface. So here the name, the problem loaded is q underscore Abacus ODB, and so is the case in Abacus interface. Just for sake of comparison, we can quickly look at the limits of this von Mises stress being displayed on both the interfaces. For that, for Abacus, you can just click on the contour plots options and then click limits. Here we can compare the max and min limits of the von Mises stress are same on both the interfaces. This is the max and this is the min. So with this feature, we can visualize the Abacus simulation results by loading the ODB file of the simulation. This brings us to the end of the first part of the training session, where we looked into the Abacus simulation using native Abacus material definitions. We run the simulations and visualize the results using both Abacus and Z-master interfaces. We now move on to the Abacus simulation using the Z-mat elastic material definition. The Z-mat file, Z-mat_elastic, is placed in the same folder as the INP file. It's an ASCII file and contains the various Z-set related keywords concerning the material definitions. As you can see here in this, these are the various keywords concerning the Z-mat material definition. Here it's behavior, which is linear elastic, and the properties, the material properties that are used here are Young's modulus and Poisson ratio. We use the same values for Young's modulus and Poisson ratio as the native Abacus simulation that we executed in the first part of this training session. Here we use a Z-set feature called Z-preload followed by the name of the Z-mat material file. Z-preload program shows the material variables and their associated Abacus output variables. So when you run this command in the command prompt, we see that it has given some output on the screen. So here it gives a list of flux name, which is nothing but the stresses, grad name, which is nothing but the strains, and here you can see that it gives the equivalent Abacus variable names, which is nothing but for EEL is nothing but the elastic strains SDV1 and elastic strain 2 component is known as SDV2 and so on. And not only that, the Z-preload also prints out the Abacus material section block that needs to be used in the Abacus input file. So this is the material section block that goes into the Abacus input file. Let's have a look into the Abacus input file. So on the right you have this, and here, yeah, you can see that this particular block, which is an output of the Z-preload command. So this material section block, which is an output of the Z-preload command, is used in the input file, Abacus input file, as you can see here on the right. Yeah. So you have the material name as Z-mat elastic, and then the dep var, which is nothing but the dependent variables in this case, which is 6, and since it's a user material, the number of constants are 1, and then this is how we can use the same block of material definition in the input file in order to use the Z material model definition in the Abacus simulation. This particular block can also be visualized in the CAE. So let's load the input file, that is the Abacus model. Now in this case it is Z Abacus elastic, which is using Z-mat. So as mentioned earlier, the mesh is exactly the same. The only difference is that now we use a different material definition. Instead of native Abacus material definition, we use Z-mat elastic material definition. So in this case, when you double click this, you can see that you have these material behaviors called dependent variables, and it's a user material. The number of constants are 0, and then the number of solution state dependent variables are nothing but 6 in this case. That's how the Z-preload command is a very useful feature where you can preload a material Z-mat material file definition and then have its equivalent Abacus names, like in this case it's SDV1, SDV2, SDV6, and so on, and also the block here. In the first section of the training session, we have seen that the Abacus simulation using the native Abacus material definition is launched using the Abacus command from the command prompt. However, the conventional way of launching an Abacus simulation that uses a user-defined material is by using a particular switch called user that points to the UMAT photon file. However, the Abacus in simulation interface with Z-mat material does not require a photon file, but instead a precompiled Z-material integration object file is used. Just for the sake of completion or illustration, we can verify that the standard way of launching Abacus simulation with a user-defined material does not work. As you can see here, we have launched the Abacus simulation for the input file using that is interfaced with the Z-mat material. And when you launch the command here, you can see that it says an Abacus error, saying that the Abacus standard analysis exited with an error. And in order to see what the error is about, we could actually refer to the message file that it has printed. And if you look at here, so the error states that it's a user subroutine UMAT is missing. So like I've mentioned, the conventional way of launching the Abacus simulation, which is using a external or a user-defined material, does not work. So in order to launch an Abacus simulation that uses a user-defined material, in our case it's a Z-mat material, we have a specific command called Z-mat. And the syntax of this command is as seen on the screen here. You have Z-mat followed by a switch called FG, which is equivalent to the Abacus switch interactive, and then followed by the name of the input file that you want to, of the simulation file that you want to simulate. So here we can see that the simulation is being launched, and here in the background you can see that there are all the Z-set related DLLs that have been loaded. And then, as I've mentioned earlier, for Abacus simulation that uses an external material definition, you need a special switch called user pointing to a photon file. But in our case, since it's interfaced with Z-set or Z-mat, it points to a object file concerning the Z material integration. As you can see here, it proceeds further with the execution, and here you can see the Abacus being launched. And apart from the standard way of executing Abacus, here additionally we can see that the behavior, that is the Z-mat material behavior, is being read from the material file that we have used. And also it also kind of gives output like that of the Z preload, where it prints out the various variable names and the associated Abacus names, and at the end it says that the Abacus job has been completed. Now that we have looked into the way of running an Abacus simulation interfaced with the Z-mat material, let us now quickly compare the results of both the native Abacus simulation and the Abacus simulation that is interfaced with the Z-mat material definitions. So let's do it. So here, first on the left side of the Abacus window, let's select the simulation concerning the native Abacus simulation. That is the ODB of the native Abacus simulation. And similarly on the right, let's open the ODB of the Abacus simulation that is interfaced with Z-mat material definitions, that is Q Abacus Z-mat elastic. So here we can quickly select the fields, and so we'll do the same thing here. As you can see here on both the left and right windows of Abacus, we can see that we have exactly the same results. So here what we have done is we are just trying to compare the results obtained by the simulations, two Abacus simulations, the one which uses the native Abacus material definitions, and the other one that uses the Z-mat material interface definitions. In both the case, we represent the same material properties of Young's modulus and Poisson ratio, and here we see that the results are exactly the same. This brings us to the end of the second part of the Z-mat Abacus training session. Before we move on to the third and last part of this training, I would like to summarize what we have done so far. In the first part of the session, we have looked into running an simple Abacus simulation using elastic material properties. In the second part of the session, we set up the same Abacus simulation but using the Z-mat elastic material definitions. We have discussed how we can run such an Abacus simulation that uses Z-mat as a user-defined material. We also looked into how the Abacus results database file, that is the ODB file, can be visualized with the Z-master interface. So now in the third part of the session, we run an Abacus simulation using a nonlinear material model using the Z-mat Abacus interface. For the demonstration of nonlinear material simulation, we use the generalized elasto-viscoplastic material model from Z-mat. As you can see here on the screen, the material is characterized by kinematic nonlinear potentials along with isotropic constant parameters, as well as we use the Norton flow rule for this potential, and the criterion here is Mises. Along with that, you have your standard elastic material parameters like Young's modulus and Poisson ratio. We now do the Z preload of the material. Let's do it. Z preload of this material, which is Z-mat underscore plastic. As you can see here, it has printed the preload of this Z-mat material, nonlinear material. Unlike the elastic material, which has 6 dependent variables, here the nonlinear material has 25 dependent variables, and here you can see the mapping between the Abacus names and that of the Z-mat names. You have SDV1 until 19, and you also have some auxiliary variables which are named from SDV22 unto SDV25, SDV22, SDV25. And so yes, this is what the Z preload of the nonlinear material tells us about. We now launch the Abacus cube simulation that uses the Z-mat nonlinear material that we have just seen. And as mentioned earlier, in order to launch the Abacus simulation, we use the Z-mat command as Abacus using Z-mat as a user-defined material. So in this case, let's launch the simulation here. As you can see, right from the earlier simulation of elastic material model, it is done in the same way. And here, as you can see, it has also executed the Z preload in the background as a part of the Abacus simulation run. And here it says it has done reading the material file. In this case, it's the Z-mat material file, the plastic material file. Here it also talks about 25 state dependent variables, that is SDVs. And here you can see Abacus job completed. We can now visualize the results, Abacus results, using the ZODB, that is the Z master interface. You can see here the Z master window has been opened. Here this is the mesh. Then you can click on the FAA results here. Visualize the fields. Since it's Abacus, nonlinear material simulation, you can see all these names where you have SDV1, SDV2, and for an equivalent names of, as to what these SDVs refer, you can actually use the output of Z preload that we have already seen. So here we see as it's a non as it is a non-linear material simulation, you have many of these Abacus variables, that is SDV1, SDV2, so on. And just in case we would want to know what these names actually refer in terms of ZZ, it's, for example, since it's a plastic material or a non-linear material, what we can see is we would be interested to see the plastic deformation, that is in this case EV here on the right, which you can see here. EV now is nothing but SDV7 here in this case. So we can click on SDV7. So here this is nothing but the plastic strain or the accumulated plastic strain and so on. So basically this is how you can visualize your results. Not only run an Abacus simulation which is interfaced with Z-mat, but also visualize the results using the Z-master interface. So this brings us to the end of the training session. And in this training session, we have looked into the Z-mat Abacus interface using examples of both elastic linear materials and plastic non-linear materials. We have also visualized the Abacus results using Z-master GUI. And so for any further queries, you can reach out to the ZZ support team at the email shown on the screen. Thank you.